All right, so this is section 3.6, and we are going to be looking at zeros of polynomials and specifically what is called the rational zero theorem or rational root theorem. So if we are continuing on our journey of looking at polynomials and trying to figure out what their graphs look like, one of the things we will need to do is to be able to find what their roots are or where it crosses the x-axis. And so we are going to be using this rational root theorem. If I have a polynomial that I can't factor, that is really long and really big, and I don't have any tools for factoring it or solving it, then what we can do is use what's called the rational root theorem or rational zero theorem. And this gives us a list of numbers to try. So otherwise, I would be looking at all of the numbers that exist and trying those. So this gives us a narrowed down list of possible rational roots. Now, if you recall, a rational number is a number that can be written as a fraction. So we want numbers, or we're referring to numbers that can be written as a fraction or a terminating decimal, or repeating decimal. And so these rational roots are going to give us a list of numbers that we can plug into our function. And then we're going to be using the factor theorem that we kind of talked about in the last video. And if I plug in these values that I'm testing and they equal 0 when I plug them into my function, then that means that that factor is a root and we can go ahead and divide by it. So the other thing we're going to be using is that the total number of roots that I have should be equal to the degree of the polynomial. So if I have a fourth degree polynomial, I should have 4 roots. That may include some multiplicities, may include some imaginary roots, but that should be the total number of roots that I have. Okay, so the rational root theorem. What we're going to be looking at is the factors of the constant, this number on the end with no variable on it, over the factors of the leading coefficient, the number next to or in front of the x with the largest exponent. So this first 2 examples, we're just listing the possible roots, or rational roots. So my constant is 4, and my leading coefficient is -1. Now, for all of these, I'm going to want the positive and negative version of each of them. So positive -1. 4 is also divisible by 2 and 4. And those are all of the factors of 4. -1 just has positive and -1. So I need all these combinations, 1 over 1, 2 over 1, 4 over 1. And that would just be positive and -1, positive, -2, positive, and -4. And those are all of the possible rational roots. So what we would do if this were a problem where we were asked to actually find all of the roots is we would plug these values into our function and see which ones equal 0. For our next example, our constant on the end is -2 and our leading coefficient is 15. All of the roots of 2, or all of the factors of 2 are positive -1, positive -2. But 15, it's positive -1, positive -3, positive and -5, positive and -15. 15 is divisible by all of those numbers. So I need to come up with every combination here. I need 1 over 1, 1 over 3, 1 over 5, 1 over 15. I need 2 over 1, 2 over 3, 2 over 5, 2 over 15. So plus or minus 1, plus or minus 1/3, plus or minus 1/5, plus or minus 1 over 15, and then plus or minus 2 over 1, which is 2, plus or minus 2 over 3, plus or minus 2 over 5, and plus or minus 2 over 15. And those are all of the possible rational roots that I could plug into my function and see if they actually give me a root. So now we're actually going to try and find the roots. So here it says find all the zeros. So now we need to actually try and find them, not just find the possible ones. But that is where we will start. Now this is a degree 3 polynomial. So when I'm doing these problems right off the bat, I just make a box off to the side. And this is kind of my reminder to myself that I should have 3 x's. I should have 3 roots that I find. So I have my constant, which is 6, and my leading coefficient, which is 1. So all of my possible rational roots are 1, 2, 3, and 6. And so what we're going to do at this point is now plug these into our function. So I have plugging in 1, plugging in -1, plugging in 2, plugging in -2. And when I plug in 1, 1 cubed is 1. 1 squared is 1 times 2 is 2. Minus 5 times 1, which is 5, minus 6. Well, that's not equal to 0, so I'm not interested in that one. I need to plug in -1. Plugging in -1, I have -1 cubed is -1. And then -1 squared is 1 plus 2, or times +2 is +2. -1 times 5 is +5, and then -6. And that does equal 0. So we have found one that works. So we just found one of our x's. If it's plugged into 0, then that means it's a factor or it's a root of that polynomial. And once I find one that works, I can divide using synthetic division and see what my smaller polynomial is. So bringing down my 1, -1 times 1 is -1. 2 plus -1 is 1. -1 times 1 is -1. -5 plus -1 is -6. -1 times -6 is +6, and we get a remainder of 0, which is what we expected because it is a root. It should divide evenly. And the polynomial that I'm left with is x squared plus x minus 6 equals 0. And that's a quadratic, so I can use whatever tools I have for quadratic functions on this example now. So I can use the x method, I could try the quadratic formula. I know this will factor with the x method, so I'm going to do that. And I have -6 times 1 is -6, and +1 on bottom. +3 and -2 give me -6 multiplied and then add to +1. So I'm left with x plus 3 and x minus 2. So x equals -3 and x equals 2. And those are my last two roots. Okay. Now, going back to the original question, this is 4 terms. And previously we would have said, oh, 4 terms, I should think factoring by grouping. And you can absolutely still use those tools. But if I tried factoring by grouping here, it wouldn't have worked. I wouldn't have been able to get anything grouped together and pull out the same common factor. So on to number 2 here. So here again, we have a polynomial and degree 3. So I'm going to set up my box off to the side just as my reminder to myself that I should get 3 answers here. And again, it's 4 terms. I could try factoring by grouping, but factoring by grouping will not work. So I can go ahead and use the rational root theorem. I have -3 over 1. So that's going to be positive -1, positive -3. And those are all the numbers I could try. And then if none of those work, then I have no real roots and I have to figure out something else. So plugging in -1, -1 cubed is -1. -1 squared is 1 times 7 is +7. -1 minus 11, and then -3, and that is not equal to 0. Plugging in +1, that would be 1 plus 7 plus 11 minus 3, and that is also not equal to 0. Plugging in 3, I have 27, and then I have plus 63, and plus 33, and then -3, and that is also not equal to 0. And then plugging in -3, let's see if that works. So plugging in -3, -3 cubed is -27. -3 squared is 9, plus 7 is 63. And then -3 times 11 is -33, and then -3. And that does equal 0. So we found our first root. And then we can go ahead and use synthetic division to divide. So -3, and then I have 1, 7, 11, -3. Bringing down my 1, -3 times 1 is -3. 7 plus -3 is 4. -3 times 4 is -12. -1, 3, and 0, which is what we would expect. We want it to have a remainder of 0 because it should divide evenly. And I'm left with x squared plus 4 minus 1 equals 0. And 4x. And that is not something that the x method will work for. We could try, but we're not going to be able to find numbers. So since it is quadratic still, I can use the quadratic formula. So -b, which in this case is 4, minus or plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. All right, so this gives us -4 plus or minus, and I have -1 times -4 becomes a +4. 16 plus 4 is 20, and the square root of 20 can be rewritten as 2 root 5 because we can pull the 4 out. So plus or minus 2 root 5 over 2. I can simplify this. -4 over 2 plus or minus 2 root 5 over 2. And those can simplify to -2. Those can reduce, plus or minus root 5. Now, if I had an even number in here, I could not reduce with a number on the outside. So I could not reduce with 2 here and this being even. But I can reduce with the numbers out front. So my last two roots are -2 plus square root 5 and -2 minus the square root of 5. Okay, so our next example has a degree 4 polynomial. So that means I should have 4 answers. And our constant is 24. And our leading coefficient is 1. So, and I've made all of these with the bottom number of 1, so we didn't have to deal with any fractions in here. You might have some examples where you do have a number down here and you have to end up trying fractions. But I've chosen ones that are nicer for getting started on this. Factors of 24 would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. So kind of a long list, but we can start off with plugging in 1 and -1. And you just kind of start off and hope to find something and then divide and get a smaller polynomial and kind of go from there. So if we plug in 1, then I end up with 1 minus 6 minus 8 plus 24. That does not equal 0. If I plug in -1, I have 1 and then minus 6 plus 8 plus 24. That does not equal 0. I can try 2. Plugging in 2, I have 16 minus 24 minus 16 plus 24. And that one does equal 0. So that one works. We have a root of 2. So I can go ahead and divide. And notice here that we have no x cubed term, so I need a placeholder. So I have 1, 0 for my placeholder, -6, -8, and 24. Bringing down my 1, 2 times 1 is 2, 0 plus 2 is 2, 2 times 2 is 4, -6 plus 4 is -2, 2 times -2 is -4, -8 plus -4 is -12, 2 times -12 is -24, and we get a remainder of 0, which is what we would hope to see. But what I'm left with is still a cubic polynomial. And so it's not a quadratic. It's not something that I can use the x method for. It's not something I can use factoring by grouping for because it won't be able to pull up the same factors. But I can still use the rational root theorem. I can still try more values here. So, because my ending number is 12 now, I can get rid of anything that 12 is not divisible by. So 12 is not divisible by 24, and works. So I can get rid of 24. I can get rid of 8, and that's it. And I've already tried 1 and -1, and if those did not work for the original polynomial, then they wouldn't work for the smaller one either. So I'm left with these other numbers that I can keep plugging in and trying. And even though we already tried 2, I can try 2 again because it is possible for us to have a multiplicity of 2. So I could have 2 copies of that root. Now I'm going to plug in to this smaller polynomial here, and I'm going to plug in 2 again. And so plugging in 2 to this smaller polynomial, 2 cubed is 8, and 2 squared is 4 times 2 is 8, minus 2 times 2 is 4, minus 12, and that does actually equal 0. So that means we do have another copy or a multiplicity of 2 for this root. So I can go ahead and divide this smaller polynomial now by 2. 1, 2, -2, -12. Bringing down the 1. 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is 8. -2 plus 8 is 6. 2 times 6 is 12. And a remainder of 0, which is what we would expect. And I'm left with x squared plus 4x plus 6 equals 0. So now I have a quadratic. Now I can use those methods that I know. So x method, quadratic formula, all of that. I could try the x method, but it's not going to work. So I'm going to go ahead and go straight into the quadratic formula. Negative b, so -4 plus or minus the square root of b squared, so 16 minus 4 times a times c, all over 2 times a. Well, -4 plus or minus, and I have 4 times 6 is 24. 16 minus 24 is the square root of -8, and so we have imaginary numbers. So I have this -8 in here. I can rewrite that as -4 plus or minus 2i root 2 over 2. And I can reduce that, and that ends up being -2 plus or minus I root 2. So my last two x's here are -2 plus I root 2 and -2 minus I root 2. And so, since these are imaginary, these are two places where our graph does not actually cross the x-axis. It looks like they're, or they are imaginary or complex roots. So it only actually touches the x-axis in these, or at this spot here. So there's a couple important notes here at the bottom. As we just saw with those last two examples, irrational zeros and imaginary zeros always come in pairs. So if you have a plus the square root of b, you also have a minus the square root of b. And we saw that in how this happened here in the previous example. So we had -2 plus root 5, -2 minus root 5. And that's because of the quadratic formula and that plus or minus sign. And for the same reason, the same is true with imaginary zeros. They always come in pairs. If we have a plus bi, we also have a minus bi as a 0. You can't just have one imaginary or one irrational root. So same thing like we just saw here with the quadratic formula, the plus or minus sign, those will always come in pairs. Okay. And we've already been using this, but that our polynomial has n complex roots. So the number of answers we got should have been the same as the degree of our polynomial. So a couple last notes on this section. The fundamental theorem of algebra says that every polynomial or every polynomial of degree n greater than 0, so as long as it's not constant, has at least one complex root. So it can be an imaginary root. It doesn't have to actually have anything that touches the x-axis. But it is possible, or it is ensured that we will have at least one root, whether it's imaginary or real. So the linear factorization theorem basically just says that any polynomial can be broken down into linear factors, whether those again are complex numbers or real numbers. And so what we're going to do in this next example is kind of go backwards from what we were just doing. We were given a polynomial and asked to find the roots. Now we're going to be given the roots and we need to find what was that original polynomial. Here it has the zeros listed off and I got capitalized. So this should actually look like imaginary I here, not capital I. But we also know that if I have I here, it says find a fourth degree polynomial. So meaning we should have 4 roots with real coefficients that has zeros of -3, 2, I. And because it's fourth degree, I should have 4 of these. And if I have I also have -I. And then they also tell us a point here. This is an X and a Y value. So what we're going to do is try and find this polynomial. Now, I don't know what that coefficient out front might be, but I do know these 4 roots, so I can write x plus 3 for -3, and then x minus 2 for 2, and then x minus I for positive I, and then x plus I for -I. And I need to just start multiplying these out. I'll do a box multiplying these 2 out just so you can see how that works, and then I won't do the other box. So I have x minus I and x plus I. So that's x squared, -xi, positive xi, and -I squared. But I squared is -1 times a negative would be +1. Well, -xi and positive xi cancel out, and these 2 factors here become x squared plus 1. If I multiply these 2 out, I end up with x squared plus 5x plus 6. And now I need to multiply these 2 out. I'll go ahead and just do that box really fast off to the side so that you can see it. X squared plus 1 and x squared plus 5x plus 6. X to the 4th power, 5x cubed, 6x squared, 6, 5x, and x squared. So I have a times x to the 4th plus 5x cubed plus 7x squared plus 5x plus 6. And I know a point that I can plug in. So I have the point to -2, 100. So that -2 is an x value and that 100 is my y value. And -2 to the 4th power is 16. -2 cubed is -8 times 5 is -40. -2 squared is 4, so plus 28. And then minus 10 and plus 6. So let's total all of that up here. And let's see. We have 16 minus 40 plus 28 minus 10 plus 6. Work out that way. Let me double check that because I'm getting that that's equal to 0 and it should not equal 0. So let's see. -2 to the 16, or -2 to the 4th is 16. And then -2, 8, -40, and then interesting. You know what? I'll edit this problem and we will end this video here, and then we will come back in part 2 of this section and fix this problem here.